6A, the nature of energy. 6.1, energy's importance. People talk a lot about energy. Ever since the great gas shortage of the early 1970s, people have realized that there is no cheap, convenient, inexhaustible source of energy. Technologically advanced nations, including the United States, gobble up energy at ever-increasing rates, while developing countries in Asia, Africa, and South America have their own increasing energy needs. Oil-rich Middle Eastern nations use their resources for political purposes by threatening to cut off exports to more powerful enemies. Nations make energy independence an economic and political goal. So why is energy so important? Energy moves everything. Humans, animals, and plants require energy to live. Energy drives all the processes in nature that recycle water and other forms of matter. Wind and ocean currents circulate because of energy. Internal and external sources of energy heat the earth. Humans use many forms of energy for building, communicating, exploring, and conducting warfare. Without usable energy, life would not be possible, and the universe would be a vast, dark, cold, empty place. 6.2. What is energy? Energy cannot be defined any more easily than the other fundamental properties of creation. No one knows what energy is. We know only what it does or has the potential to do. It is a property of matter that can sometimes be measured, although measuring some forms of energy is very difficult or impossible with our current level of technology. Energy is a positive scalar quantity measured in joules, J. 1 joule equals 1 kilogram meter square over second square. To understand some aspects of the nature of energy, you can compare it to wealth. Having a lot of energy is like having money invested in a bank, stocks and bonds, property and possessions. Just as you may have many forms of wealth, a system may have many forms of energy that contribute to its total energy. When you buy something, you exchange some of your money for something else. Similarly, energy can be exchanged for work, matter, or other forms of energy. A system loses energy to its surroundings in the same way that you lose money when you spend it, give it away, or it is stolen. Energy is operationally defined as the ability to do work. This description doesn't define energy. It just says what it can do. Just as there are many forms of energy, there are many forms of work. For now, we will say that work is done whenever an object moves through a distance because of a force acting on it. Work and energy are interchangeable and are measured in the same unit, i.e., the joule. When the surroundings do work on a system, the system gains energy. When a system does work on its surroundings, the system loses energy. Work is discussed in detail in Chapter 7. 6.3. Potential and kinetic energy. Energy can be broadly divided into two main kinds: potential energy and kinetic energy. Potential energy. Potential energy, PE, is sometimes called the energy of position or the energy of condition. A system's potential energy can depend on its position and a force that has the potential to move the system from its current position. Some contact forces, except friction and all field forces, can generate potential energy in susceptible materials and objects. For example, a magnet can produce magnetic potential energy in a steel paperclip holding papers together. The paperclip can't move, but it has the potential to. Potential energy can also exist as a consequence of the composition or condition of the system. This principle is particularly true at the particle level. Forces in chemical bonds store energy that can do the work under the right conditions. Gasoline molecules contain chemical potential energy that is released during combustion, a change of a chemical condition. Kinetic energy. The kinetic energy, Ke, of a system is its energy of motion. All moving matter, regardless of size, has kinetic energy. Kinetic energy depends only on the system's mass and speed. The more mass an object has and the greater its speed, the greater its kinetic energy. Systems may have both potential and kinetic energy at the same time. In some situations, a system's total energy can be converted back and forth between potential and kinetic energy. The following sections discuss various forms of energy, how energy is converted, and how total energy is conserved.